Okay, today in KNES789M, we are going to cover the important topic of adding muscles to your model, making changes to the parameters of those muscles if needed, and gauging, I'll just say, the validity of the muscles that you added, or just more generally speaking, gauging whether you've added muscles that are appropriate for the model or are going to work well for the model, which are probably things you don't have much idea of how you might go about doing that right now, but that's what we will cover today. Okay, so why add muscles to the model in the first place? Well, let's take a look at our model here. And this is the 2D gait sim model that we've been working with for most of the second half of the class here. And if I zoom in here on my model, I can see that it's got two muscles that span the front of the hip here. It's got a rectus femoris muscle, that's this long one, and it's got a iliopsoas muscle, that's this shorter one here that crosses the front of the hip higher up above there. You'll see this sort of thing done pretty commonly in, especially in simpler two-dimensional type models like this, where obviously there's not just one uniarticular hip flexor muscle in the body, right? Anybody that took, musculoskeletal anatomy knows there's primarily two main muscles there. There's the iliacus muscle and there's the psoas muscle. But for a simple two-dimensional model like this, we can often get away with quote-unquote ganging conceptually similar muscles together and representing them as a combined single hypothetical muscle that kind of includes the strength and kind of the averaged properties of both of those muscles. And you can see another common example of this down here. If I look at the knee, where you can see it's only got one vasti muscle, or we talk about the knee extensors as the quadriceps, quadra meaning four, but this model's only got two quadriceps. It's got rectus femoris, and then it's got just one vasti muscle here. Okay? That doesn't mean that this is simulating a case of people that lack two of the vasti muscles, only have one. It's got one vasti muscle here that has the combined strength and combined overall properties of all three of the vasti muscles. Okay. Now, why do they do this in models like this? Why don't they model all three vasti muscles, or why didn't they model both hip flexors there? A general thumb rule that you want to take in creating your models is that you have to decide on a certain final level of model complexity that you're going to use for your model that you address your research question with, and how complex do you make the model? How complex should it be? The general thumb rule is that the model should be of the absolute minimum complexity level needed to answer the research question. Okay? The primary motivation for that is that the more complex a model gets, the harder it is to understand. The purpose of modeling is to create a simplification of the system that we're dealing with, the human body in most of our cases, and we want to strip away as much complexity as we can in order to create a modeled system that's easier to understand, or easier for us to understand. Okay? So our goal here should be making it as simple as possible, or from another perspective, only as complex as needed to address the research question. Now, when we get towards the end of the class on covering model validation, then we'll talk about some cases where maybe you might want a little bit of extra complexity in the model for gauging validity purposes. But generally speaking, you don't want to add unnecessary complexity to your model. You want it to be as simple as possible while still addressing the research question well. For example, if I wanted to study, say, knee joint loading, I would obviously want to have my quadriceps in there, because the quadriceps play a big role in the loads on the knee joint. But all four of the quadriceps muscles apply their load on the tibia and on the tibiofemoral joint through the patellar tendon. Okay? So if my goal is I just want to study the force on the knee in walking with this model, then I don't really need all four unique quadriceps muscles. I definitely want to include rectus femoris because it spans the hip and the vasti don't span the hip. But do I need all three distinct vasti muscles? Well, no, not really, right? They all three end up producing force that goes through the patellar tendon, and it's that force that gets applied to the joint and that the joint actually experiences. So for that application, it doesn't really matter how much force is coming from vastus medialis versus vastus lateralis versus vastus intermedius. We don't really care about that. It doesn't really affect the results in any appreciable way for the research question of determining the load on the knee joint. So we can reduce some complexity in our model by ganging those three vasti muscles into a single vasti muscle that has the strength of all of them, so that it can still apply, a realistic total vasti force through the patellar tendon and still get realistic knee joint forces. But I don't really need the extra complexity of having the three unique, distinct vasti muscles. And you can make a similar argument there for the hip with having a single kind of combined, ganged iliopsoas muscle versus having separate, unique iliacus muscles and psoas muscles. Okay? Sometimes I might need those distinct muscles, sometimes I might not. What's an application where I might want more distinct muscles in my model? Well, for example, if I'm studying metabolic cost, then those muscles have different properties, different strengths, different fiber compositions, things that could affect the predicted metabolic cost of my model. So when studying metabolic cost, I would argue you want to maybe err on the side of including a lot of muscles in the model, not necessarily ganging muscles together into combined muscles that don't really exist in a real body. It can be hard to parameterize those muscles for things like strength and fiber composition that have a big effect on something like metabolic cost, but don't have that big of an effect on things like knee joint loading. Also, as you expand the scope of your model to include like a full three-dimensional model where many of the movements or many of the conditions that we're interested in simulating in biomechanics involve non-negligible, non-sagittal plane motions. We might want to simulate 3D motion. Then it can be beneficial to include more muscles in the model, again, largely for purposes of realism, where those muscles will have different moment arms and will be able to more accurately and realistically control a model in 3 dimensions than having a smaller number of muscles that are supposed to kind of represent the combined strength of muscles but may not accurately represent the combined geometry of muscles. Okay, so that's our motivation for, or at least some of the motivation for adding muscles to a model. Now let's take a look here at what we already have in our 2D gate model and see what we might have to do here to convert, let me go back to OpenSim here, to convert this single uniarticular hip flexor muscle into 2 separate and distinct hip flexor muscles representing the iliacus muscle on its own and the psoas muscle on its own. So first, let's take a look at the muscles that are already in our model. And here I'm in my XML code for my gate 2D or 2dgate.osim file. Okay. So I've got a hamstrings muscle, and I've got a biceps femoris short head, got a glute max, I've got iliopsoas here. Okay. Now, like most things in adding complexity to your model, if you want to add muscles to your model, it's very difficult for me to go in here and kind of naively say, I'm just going to split this in some way into 2 muscles. I'm going to split it into iliopsoas, or so I'm going to split it into iliacus and psoas. Or it's kind of naive for me to think, I'm just going to copy this and then on my own come up with some reasonable model of iliacus if I assume that this one's close enough to psoas to just leave it like that and rename it psoas or whatever. So doing it on your own from scratch is hard and hard to technically do and hard to do well in practice. A lot easier to start with something that's already done it and already done it well and copy what they did and then fine-tune it for your particular purposes. So, like we do a lot, we will go to our more complicated model, our Rajagopal model, and we will see what they did. Now, let's just take a look at that model to see how they differ here. And it's not going to like... What's that? Looks like we're missing some bone geometry. That's okay. We just want to see the muscles. Okay, so let's hide all my muscles there, except for I want to see my hip flexors. So show me right iliacus, and show me right psoas. Okay. So this model, my Rajagopal model, has two distinct hip flexor muscles there. Okay. So I want to take its definition of those muscles from Rajagopal, and I'm simply going to copy them over to my 2D gait model. Okay. So I'm going to search for psoas, and there it is. And I will copy that whole tag there, and I will paste it over into my muscles here. And then I'm going to go back to Rajagopal, and that was what, psoas? Yeah. And then I'm also going to find iliacus. Copy that whole tag there and paste it into my model. Okay. So now I've got my two unique hip flexor muscles from Rajagopal, their psoas muscle for the right leg, and their iliacus muscle for the right leg, copied over into my 2D gait model here. Okay. Now, if only it were that simple. Sometimes it's that simple, but most of the time it's not. There'll be a number of things here that are different about the muscles that I copied over from Rajagopal, that are different from its muscles compared to the muscles that were already in my model here, that make this unlikely to work well if I were to simply just start doing simulations with this model. So like most things, it's not quite as simple as just copying the stuff over. You got to do a little bit of footwork to copy it over and edit it to make it work well for your model. So the first thing that might have jumped out as you here is the muscles that were already in my model here were de Groot-Fregly 2016 type muscles. Okay. OpenSim has a variety of muscle models built into it that you can choose from. They're just kind of subtly different formulations of the typical features of the hill muscle model. Only one of them actually works right now with Moco. It's this de Groot-Fregly 2016 hill-based muscle model. And it works because it's a model that they spend a lot of time smoothing it out in terms of the mathematics involved in it. It just doesn't have any discontinuities and things like that in it, which makes it well suited for software like Moco. So the only muscles that can be in my model here, if I want to use this in Moco, are de Groot-Fregly 2016 type muscles. Okay. So first thing I'm going to want to do is change the type of my muscles that I copied over here from Millard type muscles to de Groot-Fregly type muscles. Okay. And then change the name of the tag down here to at the bottom. And then also do that same thing for my second muscle that I copied over there. Okay. So the notion that the muscles that I copied over from Rajagopal seem to be a different type than what I defined, than what was already defined here in my model, should give me a little bit of alarm in just, kind of rotely copying those over there. Okay. So let's just kind of scroll down through these muscles and see what's similar and what's different. Okay. So here's my iliopsoas muscle that already existed in my model, and it's got some paths defined here. This is defining like the route of the muscle along the skeleton, and it's got some some graphics related business here, and then it's got some properties of the muscle defined there in terms of its strength and optimal fiber length, tendon slack length, pennation angle, all the typical things that we define for this for muscles in models like this. But when I then look at my muscles that I copied over here, okay, it's got the path. It's got some wrap objects here. I'm not real sure what that is. I don't remember seeing that in my old muscles. It's got some names that look similar here, but maybe the names aren't exactly the same in terms of the tags. It's got some, like a force length curve defined here, where I didn't see that in my other muscles that were already in this model. This seems to be just in the one I copied over. It's got force velocities. It's got quite a few things here that weren't present or aren't quite the same as what they were in my original model. Okay. So I'm going to reverse course here, and I did this on purpose to kind of show you, where you can run into trouble in just kind of rotely copying things between models. One issue with OpenSim is that it's both a blessing and a curse that OpenSim has a lot of flexibility to it. There's not just one muscle model in it, there's lots of muscle models. There's not just one way to kind of define the specifics of that muscle model. There's lots of ways of doing it. But that makes it kind of difficult sometimes to just simply take a piece from some model and move it without issue into another model. Okay? So I'm going to suggest a different approach here for defining our unique iliacus and psoas muscles. Okay? So rather than copying that whole chunk of muscle code from Rajagopal, I'm going to go back to my original model with ilio-psoas here, and I'm going to reason out that, okay, when I go down to my ilio-psoas model's code here, and it says under its path points, which is defining kind of like the route, again, that muscle takes along the skeleton, in its path points, it's calling them psoas. It's not calling them ilio-psoas or not calling them iliacus. So I'm going to infer from that, and in this case, it's a good inference if you actually look at the geometry of this muscle and the path that it takes, that they are defining this muscle in this simple 2D model with the strength of all uniarticular hip flexors, but it's being given the geometry of psoas. Okay? So I am going to rename this to psoas rather than ilio-psoas. And then I'm going to leave everything the same, except now that it's going to be two different muscles, I'm going to take away some of the strength of that muscle and put it into a second hip flexor muscle, the iliacus muscle, that I'm going to define by copying over some of the elements of Rajagopal for iliacus into the new iliacus that I'm going to create here. Okay? Now, what do I mean by some, and how do I know which ones to copy over? I want to copy over the ones that I need to define my iliacus muscle using the kind of general structure of how muscles are defined in my 2D gait model here as my guide. I just want to copy over the pieces of information from the muscle in the Rajagopal model that overlaps with what I need here in my de Groot-Fregli 2016 type muscles in our model, in the 2D gait model that we've been working with. Okay? So I'm going to copy my psoas muscle, which used to be my ilio-psoas. And I'm going to paste down below that copy, and I'm going to call it iliacus. Okay. Then I'm going to scroll down here and see what information I need to replace with information about iliacus, not psoas, from my Rajagopal model. Well, first thing I need is this set of path points. Okay? So let's go to Rajagopal and see what we got there. Probably, yeah, there's iliacus. Okay, So iliacus in the Rajagopal model is defined by 4 path points. And if you're not super clear on what those are exactly, I can take a look at that muscle in OpenSim and clear that up exactly. So let's hide psoas there so that we're just seeing iliacus. Those path points are these 4 little knots that you see here. Okay, so you see a point there, kind of maybe kind of hard to see because it's all red and kind of big. I'll zoom in a bit there. Muscle geometry here in OpenSim models is defined by specifying points like coordinate points for the muscles, and then it draws the red lines between those coordinate points to define the geometry of the muscle, the path that the muscle takes around the skeleton. Okay, so here's one point, here's another point, down here there's a third point, and down here there's a fourth point. Okay? You can't really see it because the femur's not here, but these 2 first points here are coordinates defined on the pelvis, and these 2 more distal points there are points defined on the femur. Okay? So this will cause, by having 2 points that are on the pelvis and 2 that are on the femur, this will cause the length of that muscle to change when I change my hip flexion angle. Okay? So here I'm flexing the hip, and here I'm extending the hip, and you can see that that muscle is lengthening because it wraps around the hip there. It starts with points on the pelvis and ends with points on the femur. Okay. So that's what's being defined here by defining these path points in the path point set here, the path point set object for the muscle models in the Rajagopal model or in any particular model. Okay, so they define those 4 points and those 4 coordinates here. Where did those coordinates come from? Typically, they did something like what we're doing here. They referenced them from some other model. Where did they come from in that other model? They probably referenced them from some other model. Eventually, back in times of yore, somebody referenced these from like digitizing a cadaver most of the time and getting coordinate points that way, and then these things just kind of proliferate through time in the field into being the kind of the default geometry of our default kind of generic models that we use. Okay. So let's copy these path points here for defining the geometry of iliacus in Rajagopal and move them over to our iliacus that we created here. Now, it's rarely a good idea to just like wholesale delete stuff in a model. Okay, so I'm going to paste in my path points from Rajagopal and clean up my alignment there a little bit. But I'm also going to leave my old path points for psoas here so that I can take a look at the syntax of them and see where things are similar and where things are different. So generally here, with my path points that I copied over from Rajagopal, they look pretty similar syntactically to what my 2D gate.osim model was using. It specifies a location of each one of those muscle path points as a set of coordinates and specifies the body or the reference frame that those coordinates are in. We see one difference, though, in the ones that I copied over from Rajagopal. The reference frame that these location coordinates are in was defined as a body, but in the path points for the muscles that were already in my 2D model here, and you can see this isn't unique to that muscle. This is the way that they're all done in all of the muscles in this simple 2D model we've been working with. It doesn't define a body, it defines a socket parent frame. Okay? Now, the difference here, this is one of these things in OpenSim where there's lots of different ways of doing the same thing. In this model, rather than referencing a body, they reference the path in the model's objects to that body. Okay, it's kind of like rather than referencing a file like document.doc, you reference the path on your computer to where that file is located, like users/ROS/documents/document file name or whatever. Okay? Really no rhyme or reason to doing it one way or the other. Both ways work, but you got to use just one way in just one model. So I can't use body here because that's not the way this particular model is structured, and it's not consistent with what's done for all the other muscles in the model. So I'm going to make some changes here in the code I copied over from Rajagopal so that it's consistent with the format and structure of the syntax for muscles that's used elsewhere in my model. So rather than calling these things bodies, I'm going to call them socket parent frame. And rather than referencing just the name of the body, I'm going to give it the path to that body. Okay. And then I've only got to do that once for each body that has points on it. I can just copy this for the pelvis. And then I can copy it for the femur. Name it femur. And then same deal here for the final point there. Femur. Okay. And then I can delete my old path points for psoas, because this is iliacus. And clean things up a bit. And then I've just added, at least geometrically, a muscle to my model. Okay, but remember I copied this iliacus muscle from my existing psoas muscle up here. Okay? So it's got all the same properties in terms of same strength, same fiber length, same tendon slack length, yada yada. I want to replace those with values that are appropriate, not for iliacus, but for, not for psoas, but for iliacus, the one that I copied over from Rajagopal. So let's go back to Rajagopal and see what they're doing here for iliacus. Well, they've got a max isometric force, a fiber length, a tendon slack length, a pennation angle. So I'm just going to copy all those. And then I'm going to go back to my model. And I'm going to paste them in. So replacing my copied max isometric force, optimal fiber length, tendon slack length, and pennation angle copied from this 2D model's psoas with values copied from Rajagopal's iliacus. And there we go. The rest of this stuff down here, below those four, is values of muscle parameters that you can make specific to a muscle, but for some of them, usually we do make those muscles specific, and some of them we usually don't make muscle specific. In all of the muscles in this 2D gait model that we've been working with in class, all of those parameters there, all of these ones that I have highlighted here, are not defined on a muscle-specific basis. They're using a generic model for all of the muscles in the model. This one here, the max contraction velocity, is the velocity of shortening of the fibers at which the fibers would not be able to produce any force. Typically, we'll set that at the same value for all muscles. So the way that we have that done here, setting it to 10 fiber lengths per second for all muscles in the model, is not necessarily a good or an accurate assumption, but it's at least a common assumption in the field and a consistent one that's made in these types of models. This one down here where it says tendon strain at 1 norm fiber length, that's how far the model, or that's how far the tendon in the model stretches when you load it with this muscle's max isometric force. So that's what or how far it's strained beyond its slack length here when you load it with this max isometric force. And we're assuming that that's 0.049 yada 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 2 for all tendons of all muscles in this model. Is that a good assumption? Is that a bad assumption? I would guess there's probably some tendons in the body that differ fundamentally in that compared to other tendons. But again, it's a common one that's made in this type of modeling. So at least we're not making any terribly controversial, unusual assumptions there. The one that I would say here is a little bit controversial is these activation and deactivation time constants. Those relate to how fast your muscle force is going to rise when your muscle excitation is rising, and then relatedly how fast it's going to fall when your muscle excitation is falling. Those are typically not, or at least often are not defined with values that are constant for all muscles. You'll often scale them with like muscle fiber type or something like that, or with muscle mass. But again, just to be consistent with how we're doing it, in this model, we're going to leave these at these kind of generic values for all the muscles in this model. But I just wanted to highlight there these parameters that we're not replacing. We're not replacing them because we're assuming that they're constant for all muscles in this model. Sometimes that's a good assumption, sometimes that's a bad assumption. For these other 4 ones up here, it would be a really bad assumption to say that, like, you know, all muscles in the body have the same max isometric force or same optimal fiber length, same tendon slack length, same pennation angle. Those are crazy assumptions. Nobody that has any idea what they're doing in muscle modeling would think that that's a reasonable thing to assume for a realistic model of a complex musculoskeletal system. So those things we absolutely should define on a muscle-specific basis, even for kind of a fairly simple kind of instructional purpose model like this. And we'll talk more about defining these things in a non-guessing, educated type way, and invalidating things like, or decisions like this, and making informed decisions like this towards the end of class this semester. Okay. So I copied over those parameters. The big one here that you need to be worried about when you copy stuff is typically this one, the max isometric force. Okay? If you copy over the path of a muscle, if it's from a good model like Rajagopal here, typically you don't have to worry too much about needing to fuss around with fiber length and tendon length and pennation angle. Typically for models like that Rajagopal model, they've often done quite a bit of effort in creating their model and making sure that, like, these are good values that have some reasonable basis in the scientific literature, and that jive with the muscle geometry here, such that you're not making it that the model produces ridiculous kinematics or ridiculous forces in normal situations. You do want to be careful, though, here with just copying max isometric forces from some other model, because models between different studies often make very different assumptions on the strength of the muscles and the strength of the model. Okay? So what we're going to do here is we're going to take our overall strength of our hip flexor, which used to be just a single hip flexor and had a max isometric force of 2342 newtons, and we're going to distribute that between these now 2 hip flexors that we have, this psoas and this iliacus. We're going to distribute it in the ratio that Rajagopal has here. Okay? It may turn out that they have the same strengths that our muscles have, but I think it's probably not going to turn out that way. So let's take a look at Rajagopal's iliacus, and it has 1,021 newtons of max isometric force. And then let's take a look at their psoas, and it's got 1,426 newtons. Okay. So let's just make a little Excel here. We had psoas, 1,426, and iliacus, what was that, 1,021, I think. Yeah, 1,021. Okay. So the sum of those two is 2,447. And about 58% of that goes to my psoas, and 41% of it goes to my iliacus. Okay. Then I'm going to punch in my model's total hip flexor strength there, which was what? 2342. And then I'm going to distribute about 58% of that into psoas, and about 41% into iliacus. Okay. So I'm going to change my psoas max isometric force to 1365 newtons from 2342. And I'm going to change my iliacus to, what was it, 977 newtons. Okay. All right, so you've just, if you're following along here, you've just added a muscle to your model. And it's always a good idea to make sure these things pass the eyeball test. Okay, so I'm going to close Rajagopal here. Don't save. And I'm going to open 2D Gate OSIM. And things look pretty good there. I've now got 2 hip flexor muscles instead of just 1 hip flexor muscle, so that's cool. Let's take a look at just those muscles. I'm going to hide everything except for our psoas and our iliacus. And there we are. And then especially for the one that I added, which I believe was iliacus, let's just show that only. Generally a good idea to play around with the angle of the joint that that muscle spans and just make sure that it's behaving as we expect. Okay. We can see a little bit of trouble here where if I get into deep hip extension, like beyond like, oh, I don't know, 30 degrees or so, I can see the path of that iliacus muscle start to penetrate the head of the femur there, okay, which is obviously not realistic. It should be wrapping around that, right? This muscle, or this model, this 2D gate model, is pretty simple, and I think doesn't have many or any muscle wrapping geometries defined for it. You can define wrapping geometries on models like this to give kind of more detailed, more complex geometric paths for the muscles. For simplicity's sake, we haven't done that here. If you want to make a versatile model that could simulate movements that involved a wide range of motion at the hip here, that would be a good thing to do. But this is, for our specific purposes here, just kind of simulating walking, which doesn't have that much of a range of motion. That would be an element of complexity that we may or may not actually need, and is something we should just keep in mind as a limitation of this model. It may not necessarily generate realistic muscle lengths and moment arms and realistic muscle outputs in general for the hip flexors in angles of deep hip extension. But generally speaking, it looks like our model is at least visually, kinematically behaving in a realistic way. Okay. Another thing that's good to look at is to check out the moment arm for the muscle, which can be difficult to gauge here by just looking at it, but the OpenSim plot tool is really good for that. So if you go to plot, and then for Y quantity, do moment arm, and we're interested in moment arm for right hip flexion, and then tell it which muscle we want. I'm not sure why it's not showing me any muscles here. That's frustrating. Okay. Huh. Sorry about that, guys. I'm not entirely sure why this particular model is not showing up there. So let me demonstrate that with Rajagopal. Okay, let's go to plot. Moment arm for right hip flexion. Muscles. Yeah, that's what it should look like. Anyway, then if you highlight iliacus, do close, then on the X quantity, do that angle, hip flexion. Where's my muscle here? Iliacus. Check it there. Here we go. Okay, so select the quantity on the y-axis, select the muscle you want that data for, select the quantity on the x-axis, and click Add. It will generate a plot of the moment arm for that muscle across that degree of freedom at that degree of freedom. Okay, so the moment arm for my iliacus here as a function of the hip flexion angle. So this is for the Rajagopal model that I copied this from. It'd be a good idea to also plot it for the model that we copied it to, generate that same plot, and see if you're getting not necessarily these exact same moment arms, but at least something that makes anatomical sense, a positive moment arm of hip flexion for a hip flexor muscle, at least across a reasonable range of motion of that joint for simulating the movement that we're interested in, which in this case is walking. Okay. I'm not sure why that wasn't working for the 2D gait model, but I'll investigate why that's happening and get back to you guys a little bit later. I'm not going to be able to troubleshoot it in real time today. Okay, so a couple things to finish up here. Let's go back to 2D gait. We added a hip flexor there on the right side of the model. Our poor little left side of our model here still just has one lonely little hip flexor. And we want to make a nice symmetric model here. Generally, we'll be starting, with a symmetric model and then changing it to represent certain cases or certain pathologies. So let's first make a symmetric model here that has 2 hip flexors on both sides, 4 hip flexors total. You could copy that over from Rajagopal on the left side and repeat that whole process again. A quicker and dirtier way to do that, show you one of the great tricks of modeling here in OpenSim, is I've got something on the right side and I want to copy it over to the left side. So I'm going to copy my iliacus for the right side. I'm going to copy my psoas for the left side. I'm going to scroll down here until I get to my left side iliopsoas. I'm going to give him the boot by deleting it and pasting in there instead my copies of my right side muscles. And then I just need to change some things in these right side muscles that I copied over to get them to be left side muscles. Okay? First, I want everything to be named in a reasonably recognizable way. So rather than having the left side muscles with the same names as the right side muscles, I'm going to change psoas R to psoas L. I'm going to rename my points here to psoas L, psoas L, psoas L, psoas L, psoas L. Okay. Pelvis is okay. I can leave the path as being set in the pelvis reference frame for the left muscles because there's no left or right pelvis, there's just pelvis. For the coordinate here of hip flexion, this is one of those wrapping geometries that I was mentioning earlier. For the left psoas, we want that to be the left hip flexion angle, not the right. And for the socket coordinate there, or the reference frame for this coordinate, we want it to be the again, the left hip, not the right hip. And then down here, when I get onto my points that are defined for the femur, I want that to be left and left. Okay, hard part here. In order to kind of graphically flip things from the left and the right, OpenSim's not smart enough to know that when I change it to like the left side of the body here in terms of the left frame instead of the right frame, left femur instead of right femur, that I want to like kind of mirror things and copy it. I've got to tell it how to do that on my own. How do I do that? You go to the third coordinate here, which is the Z coordinate in OpenSim, the medial lateral, side to side in the frontal plane coordinate, and stick a negative sign on the front of all the positive ones. And similarly, if it was a positive one, you would change it, or sorry, if it was a negative one already, you would change it to a positive sign. So to flip something like that, go to the Z coordinate, if you're flipping it between the left and the right side of the body, go to the z coordinate of any spatial coordinates there and change the sign on the final one. If it's positive, make it a negative. If it's a negative, make it a positive. Nice part is that everything else here can stay the same. Max isometric force, we want that to be the same between both sides. Fiber length the same, everything else the same. Okay. Then we'll do this for iliacus as well. We want that to be left side, left side, left side, left side, left side. Left femur instead of right femur, left instead of right, and then flip my z coordinate, or z coordinates for the Canadians in the room, for all of them. And I can save it, and close my model, and open it, and cross my fingers. Uh-oh. Didn't like that. Oh, I made a typo. Maybe one of you saw it, but since we're not in person, you can't shout at me. Okay, here in this conditional path point, I'm referencing the degree of freedom in the model that makes it conditional, like it's engaged at certain ranges of motion for the joint and not engaged at other ranges of motion. I said joint set, hip R, hip flexion L. Okay, that should obviously be joint set, hip L, hip flexion L. There's no hip flexion L coordinate for the right hip, there only is for the left hip. Okay. So hopefully that was my only issue. Let's see here. There we go. And let's zoom in. And now I've got what looks like two hip flexors on both sides of my model, both hips. And if I change my left hip angle there, and I see both of those hip flexors moving there. All right. Okay, so now, let me pull up a video here so you can actually see me about the photo booth. Okay, so now you've seen how to add muscles to your model. Like most things, trying to just sit down and tap that out by hand would be, I would say, a fool's errand for this type of thing. But copying it over from an existing model, or at least using an existing model plus what's already in your current model to inform how to do this is generally the way to go for this type of modeling. And we also saw how to do it on one side of the body and then copy it over quickly to the other side of the body. Now, how do you go about actually generating a simulation there? It would be similar, actually it would be basically the exact same code to how we generated a simulation previously when we added the arms, right? We were starting from the initial guess for a simulation that didn't have arms. We were then loading in our model that had the arms, creating an initial guess for a model that had arms, which is Moco's arbitrary initial guess, which generally isn't very good, but then pasting into that the values that existed for the non-arm stuff in our earlier model. Okay. You do that exact same thing here. You're going to want to start from an initial guess that didn't have those two hip flexors. Create an initial guess for your model that has those two hip flexors using the OpenSim or the Moco generate your own bad initial guess thing. But then read in your old solution and stuff in all the values from that old solution into this new model here that has the muscles. A thorny thing there is, close this, that we renamed stuff here. Okay. My model here of psoas, that used to be called iliopsoas. Okay, so a problem that we're going to run into here is we're going to reference our new model here in our MATLAB code. So here, when I run my simulation and when I'm loading in the model, I'm gonna I didn't change the name of mine, but you might change yours and rename it 2D gate hip flex muscles or something, right? So load in your model that has those 2 hip flexor muscles. Then you're going to create an initial guess for that model with the extra muscles. You're going to stuff into it the values for your previous good simulation solution that didn't have those muscles, but it's going to stuff into there, it's going to try to stuff into there at least, values for the time varying controls and states and everything for an iliopsoas muscle. And it's going to say, wait a minute, I can't do that because this model doesn't have an iliopsoas muscle, so I don't know where to put this. Your solution there is that you can figure out how to pull individual, entries out of an initial guess there and just simply delete them, or you can return this name to iliopsoas rather than psoas. Me, I'm kind of, pedantic about these sort of things. I don't like to call it iliopsoas when it's actually psoas. But if you want to keep things simplest for you, if you want to make, the simplest possible approach, you would just rename this iliopsoas and just kind of live with it having, the wrong, or at least a label here that's maybe not the most accurate or descriptive label in the world. If you're like me and you don't like that, there is a way to get it to pull out that missing element from your old guess and only stuff in all the other existing elements into your new guess. So I will leave that to you as an exercise to try to figure out. It's not terribly hard, and you can kind of figure it out by Googling around on the Moco website. If you're not familiar with the Moco website, it's, I always get there from the chat here, or from the message board. But it's this link right up here. So opensim-org.github.io, then opensim-moco-site. If you have documentation here, then you can search around there for solver options related to specifying the initial guess and working with initial guess files. And it will give you documentation there for removing elements from an initial guess and only putting some of them into a new initial guess. Okay. I am not showing you how to do that today because, not out of laziness or because I forgot how to do it, but because this is a very valuable skill to try to develop in your tool belt of modeling and simulation. Being able to figure out how to do something that seems like it should be possible, but you don't intuitively or naturally know how to do it, and going to the documentation of the website here to figure out how to do it. If you really get stuck, just ask me, I'll tell you. If you don't want to ask me, but you want to figure it out quickly, if you click on forum up here, that's the OpenSim Moco community forum. And don't search up here, that searches all of simtk.org. But if you search down here, you can search just the forum. And I'm 99% certain people have asked this question. I may even have asked this question on the forum before. And folks like Nick, who's one of the creators of Moco, have described how to do it, or in many cases have pasted like example code for how to do it in MATLAB and how to solve this exact thing. So if you really get stuck trying to do that, you can search around in here for like, how do I make a new initial guess for a model that has extra muscles or something conceptually similar to that, and see what you can find. Or if you really can't find it, you could post a new topic here and just describe specifically what you're trying to do and what you can't figure out. And generally speaking, somebody will see it and reply with a solution to it, usually within a day. This is a small community here, but it's a pretty vibrant and active community. It's pretty rare that I ask a question that I don't get a response to from somebody within a day or so. Okay, that is it for today. So try to add some muscles to your model there, copy it to the left side, and try to get a simulation going, a simulation generated in our 2D gate code that simulates walking with those 2 hip flexor muscles on each side. And that is it for today.